versus. Okay. All right. Yeah, thank you. So I will be talking about this work that was put on the archive in January this year. It was work that was started when I was still a postdoc here in 2018. So it took a long time for me to publish this. I was trying to publish. With some help from Riccardo Ratazzi, who was visiting at that time, and with Sergey. So the summary is this. So my claim is that there are medium-dependent, medium-range forces between standard model objects and particles. If those standard model particles couple to some new low-mass field quadratically. Okay, so that's the general claim. And so this new low-mass field could be just neutrinos in the standard model, dark matter, or dark radiation. So it has to be around. It has to have.
I like quadratic. You mean psi bar something or other psi. That's
Yeah.
What you mean by quadratic.
Yeah. So it has to be quadratic in the standard model particle current and quadratic in the new field. Yeah. Some biquadratic interaction. I'll give you an example in a second.
But when you are saying new, it means non-existent.
New means the standard model neutrino. So my claim is that even in the standard model, there's a new force that's much weaker than gravity, mediated by the cosmic neutrino background. So that's called the C nu V, if you wish. It mediates some force as well.
Meaning there really is a measurable force.
In
this
principle,
room.
measurable, and in practice, no. So in practice, this is, I think, too small to
I
be
see,
measured.
but and it would be between, like, give me an example, like between neutrinos.
My claim is that. Give me a second.
Yeah.
Okay. So are we good with this so far? So
No.
okay, you're not good. How? Okay. So what I mean more specifically is that the Lagrangian would be would include some coupling G, coupled to, let's say, some scalar field. This scalar field could be dark matter, but it could also be, as Glennis was saying, some fermion bilinear, let's say of neutrinos or some fermionic dark matter, coupled to standard model particles. So the size will be standard model particles. These will be electrons, neutrons, protons, for example. And so so if it's a scalar field, it would have some standard kinetic term, a free scalar field. Okay. So I'm normalizing the coupling with respect to the mass. This is a dimension -2 coupling. For neutrinos, this would be Fermi's constant of 10⁻⁵ inverse GV squared. Yes.
What about F squared psi bar side, coupling to the CMB?
F squared?
Maxwell kinetic term times psi bar side for size of standard model fermion.
That would also work.
That's
Yeah, it could be a vector as well.
So it's higher mass dimension. It's dimension 7, not dimension 6, like these Corey fermion operators. Like
Well, this technically dimension 5.
Right. I'm just comparing it to a standard model, but you might win by
Yeah, I think
energy density.
indeed it could be. I think if you have something like F mu nu with some other higher dimension coupling.
Sorry, what are these braces?
I'm just saying it could either be.
Oh, these are alternatives.
G m phi squared psi bar psi or G mu bar nu.
Okay.
But I'm just going to be talking about the scalar case for the rest of the talk. Yeah.
The scalar case is some new field
There
where
would be, yeah.
F dual or F squared is supposed to be the electromagnetic field,
Yeah, I mean,
but with like a massive photon.
okay, so the philosophy is the following. So the philosophy is that this is a new phenomenon, forces between standard model particles, and we'll use it to detect this medium, to detect this new field. Now, this would be a pretty silly way to detect the photon because we're just doing it at some ridiculous rate. But it might be some like
No, but if it
some
had
dark
some
photon.
intermediate, there was a little finite photon mass, you might get a difference in the long range. Anyway, I wasn't.
I mean, there are lower dimensional operators for dark photons that you might imagine looking for, like kinetic mixes. It's a general phenomenon. Yeah.
Can you tell us what is the motivation for this line of investigation?
Good. So the philosophy is the following. So there's a lot of new emerging technologies of precision frontier experiments, so very sensitive force experiments, atomic, molecular, and optical experiments that can do very precise measurements. And so the philosophy is to leverage those technologies to look for new physics. So it would be alternative probes of physics beyond the standard model, alternative to collider physics and absolute cosmological constraints. That's the philosophy. Yeah. So my claim is that sensitive force experiments will be a sensitive probe of certain models of dark matter, dark matter models with this interaction. Okay. So if your theory has this coupling and this field phi is around, then my claim is that there's a new potential between standard model particle psi mediated that has this form. So it goes like the coupling squared, the energy density in the new field, let's call it the energy density of dark matter. It goes like 1 over r, so 1 over separation between the particles, times some form factor that might be anisotropic. So the form factor at 0 radius is 1. Okay, so that's my claim. It goes like the coupling squared times the energy density of dark matter, and it goes like 1 over r. And this form factor depends on the phase-space distribution of particles. So let's imagine that this integral, so this integral here, this piece is 1, if there's no argument there. So this is just a normalized phase-space distribution in momentum space k. But the actual form factor has this cosine piece that I will derive in a second. Okay, so my claim is you have two particles, one at x1 here, one at x2. It has some separation vector r. This is the summary of this wave force idea. Okay, so in the limit that r goes to 0, this cosine is 1, and this 1 factor.
So the x1 and x2 are the standard model side by side.
Yeah, so this would be psi 1 here and psi 2.
And it seems like it would depend on the scale length of the potential. Are you assuming it's essentially massless?
So yeah, exactly. So because it's 1 over r, it kind of looks like a massless mediator, and I'll show you why the range is longer than you might expect. That's why I say it's a medium range force. It's a force. Good. So what is one second. What is the range of the force? The range of the force is roughly set by the spread in wavelength, the inverse spread in wavelength.
So the underlying interaction is point-like.
The underlying interaction here is point-like, and you might UV complete it, and I'll show you
Okay,
if
right,
I have time.
this is not deriving from the mediator. Okay, sorry, I was just a little confused.
So it's a medium range force. The range is roughly 1 over the spread in wavelengths. It's the typical de Broglie wavelength. Okay. Any other questions? This is the main claim. I'll derive it and then give you some numerical comparisons against other effects that necessarily occur for these models. I'll show you the parameter space. Yeah.
If I understand correctly, rho dN is the density of dark matter at the point x2. And everything is correct?
Sorry, say that again.
Rho dN is the density of dark matter at the point x2.
Well, these points will be so close together that it's the density at both. Yeah. And I'll give you some more intuition. The derivation will show the physical origin of this effect. Okay? So let's derive it. It takes 4 lines. Okay. So if you have this Lagrangian, your equation of motion is just that the Klein-Gordon equation for phi. So 0 if there was no interaction, but now in the presence of this interaction, it looks like GM times the number density of psi particles times phi itself. Okay, so that's the new classical equation of motion if you have that quadratically coupled Lagrangian. So what we'll do here now is solve it perturbatively in G. So I'm going to say phi is this sum where each phi with subscript n over phi 0 is formally of order g to the n. So I'm perturbing in the smallness of g, and I will tell you what the dimensionless expansion parameter is later. Okay? So the 0th order, so the 0th order in G, I will just say phi naught is some amplitude times cosine omega t times k dot r, right? So this will, and the phase doesn't matter. So this solves the Klein-Gordon equation to 0th order in G. So if I imagine that the right-hand side is 0, right? Just a non-relativistic plane wave with omega squared.
Your capital G is not super constant,
No, no. Think of it as like a G Fermi type of interaction. Yeah, it's the coupling constant of this biquadratic interaction. Okay. And now, okay, so this is the background plane wave, and so this potential here is between two particles. So the density right here, the density of a single particle at the origin is just this is a delta function. Okay, so I'm going to assume, let's say x1 is at the origin. So then the first order in G, now I want to solve for phi 1. I can just stare at this equation and collect terms to the leading order in phi 1. So I just get GM, this delta function at the origin, and then this background wave evaluated at the origin. Okay, and so this I can solve. So I know this background wave. I can solve this using Green's functions, and I get that phi 1 is minus GM phi naught over 4 pi r cosine omega t minus kr. So pictorially, what's going on is I have some background wave phi naught, right? So this is phi naught with some momentum k in this direction, and it's hitting x1, and x1 is scattering this wave to this equation effectively, and it's scattering some spherical wave. Okay. Now, what does x2? What does the particle at x2 feel? Well, the particle at x2 feels a potential that's g over 2 times m phi squared. So this prefactor, the psi bar psi, is like the mass of the fermion psi. So it looks in the non-relativistic limit like it has this additional phi dependent mass contribution. So this effective potential is g m over 2 phi squared. So let's say expectation value of phi squared. That's the new potential for this particle x2. So now this will include just the background wave squared, but that's always present, and you would reabsorb it into the mass of psi. It doesn't have any gradients. It has some time dependence, but if n is very large, then this frequency is very rapid, and we would time average over it and not notice it. But to leading order, this will this contains a term that's of order phi naught squared, which we would just redefine as a constant contribution to the mass. But then the leading order piece is the time average of GM phi naught phi 1. Okay, and then there's some higher order pieces as well that are higher order in G. So this is the second order piece in G because this is linear and this is leading order. And so this average here is a time and phase average over all of the waves. Okay? So now if I plug in this and time average, I get minus G squared, M squared, phi naught squared over 2 over 4 pi r cosine k dot cosine kr minus k dot r. Right? So I'm multiplying the interference, right, is like the multiplication of this blue wave pattern and this green wave pattern. And the interference of a plane wave and a spherical wave gives me this funny dependence here. And so that's exactly the form that I promised you before, right? This thing here is the energy density in phi particles. So this form here is exactly reproduced. And I've done it for a single plane wave, but if you sum over many plane waves as in a realistic dark matter phase space.
What about self-force? Maybe it's more interesting.
I'll get to that after.
Oh, you will? Okay.
Oh,
Because
so
in
self-force.
astrophysics, usually when you have a wake, you have dynamical friction. So there must be something like this here too, obviously.
Oh, self-force of x1 onto x1
Yeah.
itself. Not thought about that too carefully. I mean, there is this.
Yeah, anyway, if you didn't, maybe it's a good idea. I don't know.
Okay. Any other questions? So that's the derivation. We're done. So that's well, at least the classical derivation.
Can you reformulate all of classical physics this way, that all 1 over r potentials could potentially be caused by this mechanism underlying?
No. I think Feynman had some vague idea that this 1 over r force like this could be responsible for gravity, like some medium dependent.
No. He's saying it obviously doesn't work.
But then he immediately concludes it doesn't work. Yeah, because some interesting parts of this would be actually, yeah, let's take a look at it. So first of all, this is not necessarily a spherically symmetric force because the momentum distribution of dark matter in the lab has a preferred direction, right, towards Cygnus. And so that leads to some anisotropy of this force. Furthermore, it violates Newton's third law. So the force felt by x2 from x1 is not minus the force sourced by side 2 on side 1. And that's because some momentum is transferred to the dark matter medium, which is the dynamic of friction mechanism, if you wish. The piece of the dynamic of friction that depends on the separation between radicals. Yeah, but so it's like a massless mediator in that it's 1 over r potential or a 1 over r squared force, and the range of the force is the Broglie wavelength. So this is a classical derivation. I'm not going to show you the quantum derivation. It's very similar, but quantum mechanically, you can think of this whole process as being generated by the Feynman diagram of this being psi 1, this being psi 2, and that now there's a psi naught here, so incoming psi, and then being scattered. So phi naught gets scattered by psi 1, generates this first order perturbation in G, and then psi 2 feels the interference term of phi naught and phi 1. That's again some factor of G here. And the reason why, normally if we think about, let's say, I'll get to it in a minute, but let's imagine we had linear couplings of phi, where you could just mediate, if you just had some medium independent virtual exchange of phi, the range of this force would be the Compton wavelength, because this line is far off shell. But here, even though this is a massive field, some energy is injected, some energy and momentum is injected into this line, which very nearly cancels the pole there. So this this propagator is very nearly on shell, and therefore it has a longer range than you might have naively guessed.
It's impossible to believe that this simple thing has not been thought of in some solid state at least.
So it has. So there's a so I found this out afterwards, but there's this hypothetical superconductor called a Kohn-Luttinger. So it was proposed by Kohn from the density functional theory by Luttinger in the 50s. So they said if you have ions, I think ions in a bath in a Fermi sea of electrons. So the electron quasi-particles would be like the quadratically coupled field. In that sea, there would be an attractive force mediated, very, very much like this attractive force between ions, and that could lead to exotic forms of superconductivity. But none has ever been seen. But yeah, and I think this should happen for standard model fields. Well, it happens for cosmic neutrinos. I think this, if you have some background electromagnetic field and a bunch of dielectric balls coupled quadratically to photons as well, it should happen in such a system as well. But unfortunately, there's not, other than neutrinos, there's not sort of light dark matter, light standard model particles around for us to measure this force. You could
And neutrinos are hopeless?
Neutrinos are hopeless because G Fermi is so small. I'll show you in a minute.
What about tests of equivalence principle violation, right? Like,
Yeah, so that will be, so that class of experiments will be precisely the thing that will measure this. Yeah, yeah. This force, even in the limit that R is much smaller than the Broglie wavelength, this force now depends on the composition of particle 1 and particle 2. So yeah.
And also the direction of their separation.
Well, in the limit, so for R much less than the de Broglie wavelength, this form factor is 1, and then it does become spherically symmetric. So you only feel the anisotropy at or beyond the de Broglie wavelength. Any other questions? Okay, so then I will now compare, well, I'll do some estimates of this effect and compare it to some other phenomena. So what's the wake force on a macroscopic object? So the force would be minus the gradient of this potential that I've just shown you. Okay, doing well on time. So this force would be, this force would be G squared, rho, and then on a macroscopic target, so I'm going to imagine now a macroscopic target with radius r, that's of order the Broglie wavelength, and then some other ball with the same r, and the separation is again of order r. Okay, so wherever I have an r, I replace it with 1 over sigma k squared. So the force goes like 1 over r squared, and 1 over r squared will therefore be sigma k squared. And then the potential I calculated there is pairwise between any particle psi1 and any particle psi2 in here. But a macroscopic object has many, so in this limit, I get a coherent enhancement by the number of particles in 1 times the number of particles in some. So the size of the force is roughly this. Okay, and let's put some numbers to that. So this is roughly 10 to the minus 17 Newton, so 10 attonewtons if R is about a millimeter. For reference, this corresponds to so 1 over m sigma v, right? So I put the radius of the object equal to the range of the force, and the range of the force is 1 over the de Broglie wavelength, or the spread in the Broglie wavelength. And we know the spread in velocity dispersion of dark matter in the Milky Way. This is about 10 minus 3c, a little bit less. And so this roughly 1 millimeter corresponds to a mass of about 1 electron volt. Okay, 1 millimeter inverse is about a milli eV, and in milli eV, yeah, this 10 minus 3 equals out to milli, and we get 1 electron volt. Okay, and I assumed that this was all of the dark matter, and I also assumed G of order GeV to the minus 2. Okay, so for example, if you plugged in, this is maybe an answer directly to your question for neutrinos. If you plugged in G equal G Fermi, that would be 10 minus 5 inverse GeV squared.
And mass will be slightly wrong.
Actually, the range of the cosmic neutrino background force is set by 1 over the temperature of the cosmic neutrino background, and it turns out that 1 over the temperature of the cosmic neutrino background is also about a millimeter.
I see.
So for neutrinos, this would be 10 orders of magnitude smaller because the coupling is 5 orders of magnitude smaller, and they don't make up all of the dark matter. It's a tiny fraction of the total dark matter, and it's furthermore not clustered locally. So for cosmic neutrinos, this is hopeless. So roughly this is, I chose these numbers to be roughly at the level of current sensitivity. So we know we can measure millimeter range forces of 10 minus 7.
Is it what this guy in Washington is doing?
Yeah, so Adelberger's group, and in fact he's now been surpassed by a group in China, have measured this level of force, 10 attonewtons at the millimeter scale.
So R was I'm sorry, capital R here was what?
R is both the separation and the size of both of the balls.
So you need, but there has to be some gradient too to that's from encoded
Yeah,
in the
so
signal.
my claim is now there will be an attractive, at short distances, there will be an attractive force. This is weaker than gravity, but nevertheless, there's a composition-dependent attractive force.
What will be the gravity between these two things? If you take two 1 millimeter
This is 10
particles?
minus 4 of gravity.
Oh, so it is very comparable
Yeah,
to gravity.
yeah,
I see.
So if
And
you-
those people, Adelberger and people in China, are actually measuring forces between 1
Yeah.
millimeter
So
particles?
if you do F gravity, let's say F Newtonian gravity, right? This would be G Newton. Let's say M proton, M psi over sigma k cubed. Let me just write it in the same form. So it would be that and sigma k squared. Yeah, so the figure of merit to compare between the two forces, so these both enjoy this coherent enhancement, but the dimensionless number parameterizing the strength for the wake force is g squared times rho dark matter, and for gravity, it's this. So the dimensionless strength of gravity is roughly 10 minus 38, right? M proton squared divided by M Planck squared. So now you have to compete with that small number. And then furthermore, we have measured the gravitational force at a millimeter to about 10 minus 4 precision. And so this number, this gravitational force is 10 minus 13 newtons.
But of course, your choice of the coupling constant is totally arbitrary, right?
Yeah. So
it's not like you have ruled out 1 electron volt dark matter, right?
My claim is that, okay, I will show you the plot. So here I'm plotting this coupling, G. This is why I cheated. Coupling G is a function of mass, okay? And so roughly when G is 100 inverse GV, then this quantity is of order the gravitational strength. Okay, so roughly when G is 100. But the fact that we've measured gravity at the millimeter scale, so roughly 1 electron volt is here. So this line here, because we've measured gravity 10⁻⁴ precision, we can go 2 orders of magnitude in coupling lower than that. So current millimeter range force experiments have ruled out, this is torsion balance, existing already performed torsion balance experiments have ruled out roughly this parameter space. And then at higher masses it decouples like that. Yeah, but so my claim is that those experiments have already ruled out EV scale dark matter with couplings that are roughly this value. Yeah.
What about astrophysical tests of equivalence principle violation, like lunar ranging or neutron star binaries, that kind of thing?
Yeah, good.
I mean, people place
I
limits
think
using-
they're irrelevant. So I think these are really only short range forces ever. So yeah, let me get to it in a second. Skipping too far.
It's just context for your name, your word medium range up there.
Yes.
Medium range from your perspective, not from mine.
Right. So yeah. Good. If you want the force, let me not skip ahead. I'll show you. Let me finish with these comparisons. Okay. So the second thing you might imagine is a scattering force, or just scattering in general. Okay. So normally when we think about dark matter detection, what we think about is, let's say some vat of xenon of nucleons, and dark matter comes in and scatters off your target, right? So it gives a recoil energy to psi, and then we detect this individually recoiled psi particle. The cross section, the elastic scattering cross section, is g squared m squared over 4 pi. Okay, and so for reference, the cross sections I've been telling you about. So at 1 electron volt and g of inverse GeV squared, this would be 10⁻47 centimeters squared. Okay, so this is lower than any cross section that we've ever constrained in a dark matter experiment. Furthermore, at 1 electron volt, the recoil energy of a nucleus would be sub milli eV, and we cannot see such small recoil energies. Those are within the thermal background. Milli eV is about 10 Kelvin or so. Energy. Okay, so individual scatterings for such low mass dark matter particles are hopeless. So you have to look for collective effects. There are still collective elastic scattering effects, very similar to if you're driving in a car and you stick your hand out of the window. There's collective effects, collective scattering effects, and so roughly the force of that goes like the typical momentum transfer, K, times the scattering rate, gamma. So that will be K bar. Scattering rate is the number density of dark matter particles. This elastic scattering cross section times the mean velocity v. And so if you put this all together, you get, in fact, again, the same force. I'm going to assume that K bar is of order sigma K, which is true for dark matter. So the mean velocity through the dark matter halo is of order the velocity dispersion. So if you have a large object, again, of order to the Broglie wavelength, you actually find that sort of the mean force, so this DC force of phi particles collectively scattering just on it. So this would be equivalent to just a single ball, right, of radius r, of order 1 over sigma k. Is, and there's some mean velocity of dark matter hitting your ball. This will produce in this dark matter wind some effective force this way, roughly of this size. So it's parametrically the same force as this wave force that I've described previously. However, I think this is easier to look for, because what you can do in torsion balance experiments is jiggle this ball, like force it in and out, and look for time varying effects. A DC force like this is incredibly difficult to look for from systematic background perspective. So I think this is the easier one to look for, although this is in principle present as well.
And I think the torsion balance has like blades of different material that swing past each other, and he is looking for a phase locked.
Exactly,
signal.
exactly. Because this DC force is very difficult to distinguish from any sort of gravitational gradient background in your lab. And in fact, they call it shimming, they try to zero that out. Okay.
I mean, if your neutrons and protons had the same coupling, electrons had all the same coupling, then you wouldn't see anything, I guess. I'm a little confused why we're not seeing,
So what, for this one?
no, for the
Wait.
torsion balance.
So yeah, you might imagine tuning the
other
couplings.
things.
You might imagine tuning the couplings so that the weak equivalence principle is, accidentally obeyed by this weird coupling. If
I mean,
you
it would be generic, wouldn't it, if all the quarks had the same?
approximately, yeah. So then but what you could still do is look for deviations from the inverse square law of the force,
Right.
which this necessarily has. But if you imagine there's no strong violation of the weak equivalence principle, then these bounds would decouple here. So then you would have to scratch out that regime. But everywhere in here, you would still have deviations from the inverse square law. Yeah, that's right.
Maybe it will slow down stellar dust.
No,
Oh, you tried it?
it's too small. It's too small.
All right.
Yeah, I couldn't find astrophysical applications.
All right.
Okay. Good. Other comparisons. So the next one is vacuum forces. Okay, so imagine what would happen if the field phi was not around. So let's say it had that coupling, but it was not part of the dark matter.
Hey, Ken?
Yeah.
For this DC force?
Yeah.
What if you like for torque?
Yeah, like build a propeller.
Build a windmill.
Yeah. I mean, the torsion balances effectively look. Oh, the
For
DC.
that.
DC force.
We
Yeah.
should be able to get that. So you would rotate a propeller and it would start spinning in certain orientations.
No, because
I think the
it's
torque
it's buried in the
Yeah,
dark
there
matter.
would not
so
be a
you
torque
can't
on a
make
propeller.
You
I
can't
don't
make
think
a thing that prevents the dark matter wave from going through it.
Yeah, I don't think there would be a torque if you had just. Yeah, I don't. There's no.
There's a dark matter wind, right? And
Yeah.
it's
I mean,
just
this suggests there's
collective
one
effects.
momentum down.
Let's talk about it after. I don't think there's a torque.
We want to sail. We want to build a sailboat.
I think you need some amount of like CP or T violation for that, and I don't think there is one. Right? What makes it spin this way versus that way? I don't think
Elastic
there's.
scattering, you can do it.
Yeah, it's a twist of the propeller that makes it spin.
Yeah. Okay.
Too
far out
It's immersed in
Flow in a
Uh,
certain direction.
Okay, so even if the particle is not around, there would be forces mediated between two particles, psi 1 and psi 2, from an exchange of a loop of phi. So this potential would scale like, again, quadratic in the coupling. There would be two couplings here, and it would scale like m squared over 4 pi cubed. The extra two factors of 4 pi is because it's a loop. R cubed, and the range is roughly half the Compton wavelength. Okay, so this had been computed, a long time ago in the past. And so let's compare this force relative to the wake force, or the wake potential. If I take the ratio of these two, what I find is that the wake force is enhanced by the number of particles within one Compton volume. And it's also not suppressed by a loop factor, so there's 16 pi squared. So this would be evaluated at R of half the Compton wavelength. Okay, so for low mass particles, where this number can be huge, the wake force is bigger than this vacuum force. force. Furthermore, if let's say the mass of this particle was an electron volt, the range of this force is a micron, and we're really bad at measuring micron level forces. So if you imagine, so roughly, I said this corresponded to a range of a millimeter, and at a millimeter we've done 4 orders of magnitude better than gravity, but at a micron, so over here, the short range force experiments are many, many times worse than gravity, about 1 million times worse than gravity, because there's short range Casimir effects, electrostatic patch potentials. So yeah, so this is this can be larger for low mass particles, and for higher mass particles, you're helped by the fact that this force has a longer range than this vacuum force.
And you're talking about EV masses because you can't go lower because of
So let me tell you why low masses won't work for the wake force, because of actually for both forces, because of screening effects. So let me tell you in this box over here, screening. Okay, so let's stare at this equation of motion again. Right? What are the dynamics? Basically, the presence of some number density of standard model particles, you can think of as changing the mass, right? So now I have spatially varying mass squared, that's the bare mass squared, plus g m psi of x. Okay, so what that means is that if I now have a low energy wave, if the coupling G is large enough, then it might bounce back from this region of higher mass, right? So you might imagine that, you know, as it's approaching, let's say as it's approaching a barrier, if I draw energy, kinetic energy as a function of x, right? So it would be 0 here, and then if I inside a barrier, this looks like a barrier of height g and psi, and my wave is coming in, and it has some energy that's k squared over m, right? So if the kinetic energy is far above the barrier, then this perturbative treatment will hold. But if the energy is below the height of the kinetic energy is below the height of the barrier, I get non-perturbative screening effects, and so total reflection, for example. So it's a bit of a quick argument, but I've checked with numerical simulations that the perturbative treatment that I've just shown you, and so in particular this box over here, that form of the potential, is valid when this effective, when basically the barrier height is small compared to the typical kinetic energy. So the perturbative expansion parameter is this. So this has to be less than 1. So really, when I did this expansion here, it was really an expansion in the left-hand side here. That's the dimensionless thing that has to be less
Did you
than 1.
write because making m small makes it look like it would be easier? And you're saying it's a problem when m is small.
Yeah. So, okay, so let's plot this constraint. Well, no. If m is smaller, this is a tighter constraint, because sigma k, sigma k is really for dark matter, right? Is m times sigma v. So at low masses, this actually scales like 1 over n. Yeah, but yeah, thank you. That's a good point. So at low masses, G would have to be smaller linearly to avoid screening. So it turns out by accident that this perturbative regime, so below this long screening line, is roughly matching the experimental sensitivity. So the experimental sensitivity is about a factor of 10 better than this perturbative regime. So these constraints, I mean, so you might question them here, but below here, they're quite accurate. Yeah, and so,
And you call the main force a wake because because of your picture of it being due to this downstream
yeah, yeah.
scattering effect.
Exactly. So if you let's plot it. So if you plot what it looks like for a plane wave, right? So imagine this is my particle at the origin. I'm just going to plot this. Okay, not very fancy. So it's the potential is negative in the forward direction, so roughly within kind of a parabola. If k is going this way. Right, so the potential is negative everywhere here, and then at larger angles, it looks like larger parabolae like this, and then so roughly it alternates between positive and negative, and in the forward exactly in the forward direction, if you have a plane wave, it's a long-range force for a plane wave. But if you average over different magnitudes in all possible directions, it becomes a short-range force. So in particular, if you pick for f of k to be e to the proportional to e to the minus k squared over 2 sigma k squared, so a Gaussian random field, a Maxwell-Boltzmann distribution without a preferred direction, then the form factor is e to the minus 2 sigma k squared. And in fact, yeah, good. The reason why this constraint continues and falls off polynomially is that if now you say, you take the physical situation where this is now the mean velocity, our circular velocity through the Milky Way halo, over 2 sigma k squared. So this is a better approximation to the real dark matter distribution. Then this form factor at large distances falls off as parametrically as 1 over r squared, not exponentially anymore. So that's why you still have some sensitivity at really high masses. So 1 over sigma k squared. We're doing great on time.
Then tell us, what are the practical consequences? Like xenon experiment should never have been built or some such?
So I think, well, so existing experiments have already excluded some narrow sliver of parameter space. What I think, but I haven't told you how generic these models are. This is a higher dimensional operator with a large coupling. So you have to think about the space of models. So I think this class of experiments can look for a well-motivated class of models that I will write down now. I think so. Is there anything else I want to say? Not really. Yeah, I can tell you. Yeah, good. I'll say this. So this coupling is quite large. It's of order an inverse GeV squared, right? So this would mean there's some mass scale in this coupling, in the denominator of this coupling constant that's of order GeV, which is an energy scale that we've tested very well at colliders. But one UV completion that could give rise to that coupling over there is a model of a quadratic coupling to the Higgs field. Okay, so this would be dimension 4 operator of coupling to the Higgs boson capital H of this new field phi. And at low energies, this would give you exactly that coupling over there, basically because the Higgs is heavy, so you can integrate it out, and the Higgs couples to every particle in the standard model. So in Feynman diagram language, this integrating out kind of looks like this. where the Higgs acquires some VeV, so that induces now a linear coupling of the Higgs boson little h to phi squared, and the Higgs boson couples to every standard model particle psi. So you get effectively a phi squared psi bar psi interaction from integrating out the Higgs. And so this coupling G is roughly speaking GH m psi over m Higgs squared. Okay, this 1 over m Higgs squared is coming because there's an off-shell Higgs propagator. This coupling is GH, and this VeV times this Yukawa coupling would be the mass of psi. Okay, so that's the size of the coupling that's generated. Now, yeah, so now GH controls this big G over here. So then you might ask, okay, what are the constraints on this GH from collider physics? So one process that can happen is invisible Higgs decays. So you have to make sure that the branching ratio of the Higgs to 2 phi's is sufficiently small. So we've constrained this to be about less than 18%. So roughly this means that this little g has to be smaller than the Yukawa coupling to the bottom quark. It turns out that if you take this UV completion seriously, that the main constraint comes from not from this invisible branching ratio, but from integrating out the Higgs a different way. So another thing, if you integrate out the Higgs, that can happen is changing the quartic of phi. Okay, so now I would necessarily have a self-quartic coupling. I thought that's what you meant by self-force earlier, Andre. But so integrating out the Higgs here would now give you a minimum quartic of phi to itself of order GH squared over 16 pi squared. Okay, and that's relevant because we know dark matter is not self-interacting. We know that the self-interaction cross-section of dark matter per unit mass has to be less than roughly 1 centimeter squared per gram. Okay?
Excuse me.
Yeah.
So this term gives you a logarithmic evolution of lambda phi. This diagram.
Yeah.
So in principle, you can tune this away.
You could.
Very much like you tune away the quadratic divergent piece in the mass.
Yeah, good.
I mean, you're worrying about the logarithmic contribution to throw away the quadratic to the potential.
Okay, yes. Ricardo, of course, has noticed that this model has a severe hierarchy problem.
As long as you cancel that, then you can also get
Good.
worry, not worry about this.
Yeah, but okay, so let me then, to satisfy you and also myself, let me tell you about a very related model that would solve the quadratic hierarchy problem, but then since it's
What
self-consistent,
does the constraint on GH turn into, just quickly? Started to say.
okay.
But
Good. I will finish that thought and then answer it after. Okay, so sigma phi, the self-interaction cross-section would be lambda phi, which itself is quadratic in G, squared, I think over 128 pi squared m squared. So this is the self-interaction cross-section. So roughly, this bound is constraining 1 over, this lambda phi squared over m cubed to be less than centimeter squared per gram. In fact, what I've noticed was not taken into account in the literature is a bosonic occupation number enhancement of lambda phi to the 4th dark matter. The point being is that just like this force, right, is enhanced by the number of particles within the Broglie volume, the self force of phi itself also enjoys coherent enhancement factors. So this is roughly the number of density of phi particles over sigma k cubed. Okay, at low masses, this becomes relevant. So that plotted within this model is this purple line. So over here, this is saying the single particle cross section has to be less than a centimeter squared per gram, and then the kink roughly at an electron volt is when you have that bosonic occupation number enhancement. So roughly, if you don't want to tune away this quartic coupling, you want to live in this space, because otherwise you have to tune away the quartic to make sure the dark matter is not strongly self-interacting. Okay, but as Ricardo said, it's kind of, I worry about a small logarithmic problem of this minimum quartic size. But there's a much more severe problem in this model, in fact, also for the standard model, in that it has a hierarchy problem. So there's also this diagram, and in fact, any UV completion, at least at low energies, any coupling like this, you can always close the loop of whatever it couples to, and it would have this mass, effectively a mass correction, a delta m squared, that's whatever the coupling is, GH, times the cutoff squared over 16 pi squared. And if you take GH not too small, something that's detectable, and then a cutoff of a TeV.
Can you explain your dialogue to astronomers? Is it the same hierarchy problem
Yeah.
as with Higgs?
Yeah.
Or exactly the same?
Yeah, so it would be like a loop of top quarks. would be this diagram is the main one. A loop of top quarks for the Higgs. Okay, and but for the Higgs, it's maybe not so bad. At least, delta m Higgs would be the cutoff squared over 16 pi squared times the top u power, which is squared, which is in order 1, times a log. But for the Higgs, this is 100 GeV squared. This is at least a TeV squared, maybe 10 TeV. And there's a loop factor here. So for the Higgs, it's actually not, we talk about 1% tuning, 10⁻³ tuning. It's bad, but this is horrible, right? So I'm talking about EV masses, not so small couplings, and potentially a TeV cutoff if I don't do anything to this model. So this is really, really quite severe. But I think there's a way to avoid this issue, which is that the actual UV completion is not this, but so-called super renormalizable version, which is a linear coupling of the Higgs, a linear coupling to the Higgs, and then a cubic coupling of phi to itself. Okay, so because these are dimension +1 operators, so here phi does not have such a hierarchy problem. All the mass corrections are proportional to these coefficients themselves, and it does generate at low energies effectively such an interaction with identification that GH is roughly a phi a Higgs over the squared. Okay, but this red model here would still have self-interactions from this cubic. And so roughly,
unstable, right?
sorry?
It will be unstable because of IQ.
Would be a tunneling out of your back.
Yeah. Technically, phi, if you have this coupling, phi could decay to 2 photons, for example, or 2 neutrinos, but that's...
No, but Massimo was talking about the vacuum instability.
Yeah, but there's so indeed, this A cannot be too large for dark matter to tunnel to some other vacuum. I mean, there's still a quadratic mass. Yeah. So, and roughly that would this red model would very nearly saturate this model here too. In the 2 minutes that I have left, do I have enough for the sensitivity estimate? Well, I'll just draw it. So roughly these, okay, Good. So the smoking gun signature of this force is that its spatial dependence is set by the dark matter velocity dispersion and our mean velocity to the galaxy. So including the direction, right? So every 12 hours, this V in the lab frame changes because the Earth is rotating. So these experiments are not limited by statistical sensitivity. So they're limited by systematic effects in the lab, like Casimir effects, DC forces in the lab. But the fact that this depends on your environment, you can use that to mitigate systematics. How much? I don't know. But if you take these torsion balance experiments and have reasonable parameters, so if you say that the quality factor of such torsion balances of the wire from which the masses are suspended has a quality factor of 10 to the 8. If you make them centimeter size masses, and if you cool down the experiment to 10 millikelvin, which they haven't done, so typically they operate at room temperature, again, because they don't care about thermal noise. But if you work out the thermal noise limited sensitivity of these experiments, it roughly gives you a sensitivity to here. So then there would be a huge chunk of parameter space of these quadratically coupled fields to the Higgs mass or to other standard model operators that you could probe with these force experiments. Unfortunately, the QCD axion has a quadratic coupling that's way, way too small, and the causing neutrino background would correspond to a sensitivity just below the bottom of this block. So unfortunately, that's far too small. I'll stop here. Thanks.
One or two questions. Andre.
Very
I
reluctant.
said Andre.
But so what, are you saying that Adelberger and the Chinese, if they change their experiments slightly, can look for this thing?
Yeah. I mean, they didn't look for it specifically. So what I've done is that I've taken this force, and I've compared it with the actual force that they look for. So the force that they look for is minus G Newton m nucleon squared over r with e to the minus times some alpha e to the minus r over lambda. Okay, so the map you can make is that the range of this force is roughly 1 over sigma k, and then maybe polynomial at large distances, and the effective alpha, you make this identification that G Newton m nucleon squared alpha is of order my G squared rho dark matter over 4
This is
pi.
too complicated. What should they do?
They have to reduce their temperature by a factor of 10 to the 4.
Well, what they should look for is really this form factor and not this e to the minus r form factor, and keep track of the orientation of their torsion balances relative
Did you
to the.
tell them so?
Not yet. The paper came out a couple of weeks ago, but I will. Yeah. So they should reanalyze their data, and then they could potentially discover something and probably improve on my blue line here, which is some tentative remapping like this.
Because they would probably be happy to
for sure.
to process their data differently.
They're already sensitive with experiments performed. I mean, even the experiments from the 90s.
So all it takes just data reprocessing.
Data reprocessing. And you could imagine optimization for this form factor.
Okay, let's thank Ken again.
Where, I mean, so let's take the